right. Thanks everybody for showing up to this fourth day of the conference. It's now 9:30 and we'll start the first presentation of the day. With me now I have Mateusz and Patrick, who will take us deep into the world of malware engineering. I'll hand it over to them now and enjoy.
All right, good morning everyone. I'm still surprised that there are so many people here because it's still early in the morning, right? We will try to make the best for it. It's a pretty exciting moment for us because it's the first time for both of us that we're here at such a huge conference, and it's also the first time that we do speaking here. So it's kind of pretty exciting. Within the next half an hour, probably we will talk about timing is everything. And it will be about memory dumping for malware analysis. And we will talk about our experience with it from the past. We just want to share it with you. Hopefully, basically everybody can get some information out of it. So, very quick introduction for us. This is my colleague Mateusz. I'm Patrick. We both joined VMRay back in 2019. If you haven't heard of VMRay before, please feel free to stop by our booth at the ground floor. Our colleagues there will be very happy to give an introduction to what we're doing. And parts of our daily business are basically malware analysis. We do reverse engineering. We do monitoring the threat landscape. We do family monitoring, basically. And out of the information we get from there, we are developing configuration extractor for malware to extract IOCs. And we do also basically improve signature-based detections for those kind of families. So today we want to talk about memory dumping, and the first questions of it might be, why do we need it in general? That's somehow pretty easy to explain because malware is mostly delivered in a packed or encrypted state to its target. And the reason for it is because the author, so the threat actor, basically just does not want to get its malware, to get its software, what he developed, basically to be detected already somewhere on the delivery way, right? So he always wants that the end system is getting infected. And packing or encrypting stuff is a very popular way to just bypass those security measurements. Either they have an automated way, or either it's also pretty good protection against malware analysis. And what can we do against it? I mean, there's a simple solution, so we just can write an unpacker for each available packer. That's probably the most easiest thing. But this was used in the past, and it turned out to be very complex, and it also requires lots of maintenance, just due to the fact that there are so many different packers available. Some of them are commercial, some of them just open source, and everybody else who basically has the knowledge can write her or his own one, and that's probably the thing why those things are getting too complex. And therefore, we need a way, kind of a generic way, how we can bypass this issue, how we can approach this in a more generic way without having this high maintenance. And this is exactly the reason or the situation where memory dumping comes into place. So what is the idea of it and what are our goals with it? We just want to take the sample. We want to execute or let execute itself. And during this, there must be some way how the sample unpacks itself. And we want to let do this step by the sample itself. And once done, so basically at some certain point during the execution, the unpacking is done. The sample, basically the packer has decrypted or deobfuscated its payload. And this is exactly the point where we just want to jump into. We will find it in the process memory. We will read it out, basically, so we will dump it and write it anywhere else so that we can use it later on. This has a lot of advantages, so it makes the analysis and also detection way more easier, just due to the fact that we have access to the actual payload, so there's probably nothing encrypted anymore. We can also use signature-based detection on it to identify the family, to identify versioning and stuff like this. And we also can use malware configuration extraction based on this data because it's obviously in an unpacked state. And the goal is to get really good IOCs out of it. And to summarize this in just one simple sentence, we want to create as few high-quality memory dumps as possible, but still as many as needed. And we define a high-quality memory dump in a certain way that we say it contains valuable data for us, valuable data for an analyst, for example. So either if it's the unpacked payload, or if it's some additional data like decrypted configuration data, everything but somehow provides us some information is valuable for us. So this leads probably to the question, is memory dumping really that hard? And I guess if it would not be that hard, we may not stand here today, but it turns out that it is. There are a couple of reasons for it. So one reason is basically we need to find the correct timing. So as mentioned earlier, at a point during process execution, we want to identify when the sample has unpacked itself. So we need to find the correct time when this happened. And at that certain point of time, we just want to search it and we want to dump it. But there's a different thing and different issue, basically. It's performance. So we can also dump a lot during process execution, but this would slow down the performance in general, because for dumping process memory, you need to pause the execution, you need to read the memory, and you need to write it out. So this just slows down everything. So what we need, or what we want to have, are some kind of generic trigger events, which are somehow pretty good and of high quality, that are actually addressing those issues. So we want those events to be at the correct time, and we also want those events to bypass this, or to fix this issue with the performance. So there are already some well-known triggers out there, and they are available. They, I think, exist already a couple of years, or a long time, basically. The first one is a pretty simple one. It's just we want to dump executable memory regions when the process terminates. It's a very simple idea. It's still pretty useful. It still works, and we still use it. But it could be the case that the data we get out of it is not enough. So it can happen that, for example, the unpacked payload or any kind of additional data is not available anymore because memory regions were reused, they were overwritten, they were freed, already turned back to the operating system. So there are a couple of reasons why this can be hard. We can bypass, or we can address this issue with a different trigger, or with a different approach. So we can say, for example, instead of dumping only on process termination, we dump every time, or quite often, when memory regions are getting freed, when memory regions are getting overwritten, we just take them and we dump them. This would provide us way more memory dumps, and probably way too much of them, especially when you use frameworks underneath the execution like Java or .NET. They frequently require memory allocations. They frequently free memory, turn the memory back. So this would produce a lot of noise and end up with data we probably don't need because it's not relevant for us, because it's just used by the framework itself. But still, those two memory dumping trigger reasons are pretty good and are pretty used, but as mentioned, they might just not be enough. So there must be more we need to address certain issues which are still exist here. So to summarize the issues we have various existing approaches. They are good. We still use them, and we are happy that they are basically there. But they are, in some cases, or in a lot of cases, just not good enough. So there must be more. As mentioned before, we could end up with the issue that there are just not enough data, so we miss some important things. That could be the reason that we have too many data, so we have lots of memory dumps. We need to manually investigate them, which takes time, which is time-consuming, and we doesn't want to do that, basically. And it could also happen that those memory dumps we get have a low quality or bad quality. And bad quality for us is just if those dumps are containing data which are not relevant at all. So for example, it's just a couple of bytes which have been changed. There are some null bytes in it. This is related to any framework. So just dumps which we're not interested in should not be dumped, because this would slow down the process for us as well, as an analyst, for example. There are also some open source solutions which exist there. In most cases, they're focusing on different goals and on different approaches, but they are still can be used for memory dumping. So for example, there's PECF from #008, but please forgive me if I pronounce that name incorrectly. PECF is a tool, it's a library which can be used to dump injected payloads, because it just implements a couple of different trigger reasons of heuristics which are able to detect those process injections. And it's mainly designed, at least in its default configuration, to dump only executable regions, because in most cases, if you're interested in payloads, they are somewhere stored in executable regions, because those are executable files, those are DLLs or shellcode, so the region must somehow be flagged as executable. But this could lead to missing data as well. So for example, if the region isn't flagged as executable, the process might, or the memory might be missed, right? If we are interested in regions which are in general just only readable and writable because they only contain configuration data or stuff like this, we could miss them as well. So there's still some kind of improvement, but it always depends on what you need and what you want. A different tool is Cape Sandbox. It's a very powerful sandbox, and it's a very great tool. It focuses also on configuration and also payload extraction, so it's actually the same thing we are interested in, but it just uses a different way how this will be achieved. In Cape Sandbox, they're using some automated debugging features, which you can define by yourself. So you have kind of a rule set which matches somewhere in the memory, and then you can define debugging actions, basically, which are then just executed when those rules match. So this basically can write a rule, and when the rule matches, then the debugger will execute your definitions you defined to basically read and write the memory out of the process. But this has some pre-requirements, or it requires some steps you need to take before, because that you can write those signatures and that you can write your debugging actions, you need to know the family. You need to know the internals of the family, how it works, how it's structured. So you need to analyze it somehow beforehand already. Another thing is that, for example, updates to the malware family may also lead to missing memory dumps because some internals change and the rules maybe doesn't match anymore, or the debugging actions won't fit anymore the needs. And probably, I mean, depending on how you use it, an issue is also that debugging always slows down the whole performance of the system. Debugging is slow, and if you want to have a couple of thousand samples to be analyzed and get out a memory dump, it might be slow as well. But still, it's a very powerful feature, and it depends on the need, what you want to use it for. It's a very good solution. But we will come up with some more generic triggers, some more generic events you can use to dump process memory. And that's what we're going to talk about today. So we want to have a very small set of trigger events that cover many families. So we don't want to be family specific. We want to find only some events that apply to multiple families. We also don't want to have that there's many maintenance needed for those rules, or for those events. We want to have them with less maintenance. And the result we expect from it should be memory dumps of high quality. As mentioned before, they should contain valuable data for us. The result of it should be useful for detection and also for malware family inference. It should also be useful to develop, to get the decrypted file, basically, to get decrypted configuration files that we can have configuration extraction on them. And we also want to have the final payload because of signature-based detection and also some further manual investigation if needed. So you really get the unpacked sample. You can throw it into IDA or Git or any tool you basically want to have, and they can look at it. So the trigger events my colleague Mateusz will basically now present to you is just a couple of them. So it's a small set of them we have defined in the past, just due to timing reasons. And they should and can be useful for everyone, basically. So it's not only for sandboxes, it's not only for antivirus systems, and not only for manual analysis. So there are many different use cases, basically. Someone can use them, and we hope that this would help anyone here, basically.
Okay, so let's start with an overview of some of the triggers that work well together. We'll be basically discussing the first 4 of them, but I will also go into some details for the others. So let's start with the aggressive memory dumping of injected processes. So injection is a big part of unpacking. At least that's often the case. Basically, when the packer starts executing the payload, the packed payload, compressed, encrypted payload is somewhere in the binary, maybe in the resources and so. So when it's encrypted. It's then injected into a separate process. And we could and probably should dump it at this point, but that's often not enough. So there are often multiple stages to unpacking, and we might not get the actual payload at that point, but just a encrypted blob of data with a stub that's responsible for decrypting it. So from our experience, a good approximation is basically to wait till the process terminates, and it can be either a self-termination or if it's a sandbox, basically analysis and external timeout. And at that point, we want to dump various memory regions. So we are interested in the executable regions, obviously, to get the payload, but also in the read-write regions, because those often contain the decrypted configuration files. The next trigger, a very interesting one and very simple, is the first network behavior. It also works very well, as we'll see later. The idea is very simple. So basically, the malware, or the majority of it, will try at some point to communicate with an external server. So when we detect the communication, we want to perform a memory dump. So at that point, we expect that the malware is unpacked. It has to be in a runnable state, and also at least the address of the server, so like an URL, IP, and port, has to be somewhere in memory. So that's our expectation, and when we detect the first network behavior, we want to perform a dump of the process. So we want to dump the, again, executable regions, the read-write regions, and also the thread stacks, basically, because those also can contain decrypted configuration, URLs, and so on. So not every malware uses the heap for that. We want them all. What we do not want to dump are basically system files, so like mapped DLLs and so on, that were not modified, so just to limit the amount of data that we extract. The next one covers kind of a niche. So .NET is tricky, and especially the reflective load, which is part of the system reflection API, is hard to detect, and the other triggers might not work so well for it, just due to the overhead that .NET performs. So the API calls basically don't translate well to the low-level ones, so in the kernel 32 DLL or the NT-DLL. And it's also very powerful, so it's often used by .NET-based packers, where the payload is stored somewhere, and it's kind of a self-injection, so you can load it from memory or from file into your own process space and start executing it. It's also used as the fileless attack, so it can be downloaded directly from some server and basically loaded into memory without dropping into disk. And we want to detect that. So as I said, it does not translate well to the low-level APIs, but there is a pattern. So basically, depending on what you are monitoring, you can detect this. And at that point, we want to dump the buffer, which often contains the already unpacked payload. Finally, the next one is kind of an extension to existing triggers, so that we can rapidly add changes. So if we detect that the memory dumping is not working well, and basically maybe there's a new technique being used and the other triggers don't work well, we have the additional option to create signatures. Those shouldn't be family specific, by the way, so there's nothing that identifies the family. As a simple example, many malware families store a set of URLs somewhere in the file in an encrypted form, and those can be perhaps separated by some file separator, and that's it. So if we create a regular expression, maybe we could detect that, but that doesn't tell us what kind of malware it is. And so we want to create simple rules and then scan the memory. We do not want to scan it continuously because that's too time consuming, so we only want to scan it on certain events. Basically like when the memory is freed, overwritten, when the process terminates, and so on. And if we have a match, we basically extract the memory. If we don't have a match, then we continue with the execution. Now let's talk about some issues, because the memory dumping still will produce a lot of data. So a lot of data will obviously slow down the execution, so the execution has to be paused, the memory has to be copied out of the VM, which takes always some time. It also consumes disk space, and if you have a post-processing step, this will also be very time-consuming. So one idea is to prioritize the memory dumps, basically. So some triggers are more important than others. For example, we always want to prioritize final dumps. We want to prioritize the first network behavior dumps because those are useful. And we want to deprioritize, for example, content change, which I'll talk about soon. And we also are usually interested in memory dumps of the same region that were taken at a later time. So basically discard the earlier regions of the same memory region. The second issue is basically some size thresholds that we need to establish. So we don't want to dump memory that's too little. A lot of string manipulation functions will allocate some buffers that are a couple of bytes long. We are not really interested in those, so we have to set some limits. We also don't want to dump memory regions that are hundreds of bytes big. That will again slow down the execution and the post-processing steps. So they shouldn't be too small and they shouldn't be too large, basically. And additionally, we want to have a global limit. So let's say during an analysis, we only extract 100 megabytes of memory dumps. And if we reach that, we don't take any new memory dumps. That's obviously not really good. So we have to combine with the prioritization. And basically, if at certain point in time, we know that a first network behavior occurred, and there will be coming memory dumps, but we filled the quota, so we discard, for example, the low priority memory dumps. Now let's look at some families, some real-world examples, I guess. So basically, those are the collected agent Tesla payloads, so our internal collection. And the chart shows the division between the memory triggers. So at the memory dump, basically it can be correlated to a memory trigger, like the first network behavior. And at this point, we actually have the payload. So as we see, 46% of all the agent Tesla payloads can be detected just with the first network behavior. If we add the content change trigger, we are over 70%. Shortly about the content change. So if we monitor a memory region and there is a change in the region, we want to perform a dump. This has to be with the set of rules that we talked about previously. So used together, because otherwise we'll produce too many memory dumps. We also want to probably specify some size, some minimal size of the content changed, instead of just having like a byte change and then a memory dump. That's not very useful. The next one is, for example, Emotet, sorry. So a big one here, and just the first network behavior covers 84% of all the samples. So the trigger produces a memory dump that lets us identify this region or this file as Emotet, basically. With the addition of first execution, we cover 99% of all the samples. So there's usually a network connection for Emotet. If we get it, there is already the unpacked payload. The other is covered with first execution. So first execution, we have a memory region that maybe was only readable, writable, and now it changed to executable. And the actual execution flow was redirected to that region. Then we perform the memory dump. Here we see Lokibot, and again, the first network behavior tops the chart with 76%. And together with the first execution with just 2 triggers, we are at over 90%. We also have NanoCore, also a very popular family, widely used. And here again, the importance of the first network behavior trigger with some content change applied. The rules we cover again over 90% of the family. So yeah, we are basically at the end of our presentation. We see that some of the triggers can cover the majority of families, so especially a first network behavior, that's also my favorite one, is very useful. And if we have just a few triggers, we hopefully won't produce too many memory dumps in total, and can cover many families, malware families at once. Fewer triggers, fewer maintenance. So I hope that works, and yeah, hope that you got something out of it. And yeah, thank you for listening. And here I would also like to give special thanks to Alexander Betz and Tamas Watson, which are not here, but were also part of this this topic and were greatly involved with us. Yeah, if there are any questions, then I guess now is the time. If not, you can find us probably in the forum later, preferably after 5 p.m. when we win the CTF. And yeah, thank you.
Thank you, guys. We have time for some questions, if there are any. And if not, I know that you guys have sacrificed important CTF time to be with us here. So we'll let you get back to that. Thank you again, guys, for joining us and sharing knowledge.
Thank you. It was nice to be here.
Bye. So next presentation will be at 10:15. Please use the app to rate the different sessions here. Thank you.